All right, so we are going to discuss a concept called the law of mass action. And what this is, it's a mathematical description of equilibrium. One of the things that students often screw up is that they think that the law of mass action and the and rate laws are somehow connected to one another in terms of how you do problems. You'll see that they look similar, but it's very important that you try to keep these two things straight. Because we are going to still have exponents, we're going to have concentrations of certain components in a reaction. So it looks similar to rate laws, but it is a very different process. So be careful there. All right, so law of mass action. So I want you to think about some type of equilibrium equation or reaction. Now I'll bring one back from what we were doing the other day. Let's say we take, oh shoot, this thing is not writing well. Take HCl and we add that to water. And this is going to be an equilibrium reversible reaction. And that releases chloride ions and hydronium ions. Hey, this is not working. What's going on? I can't write AQ. That's really strange. Okay, and so if I were to look at this reaction, we could treat this reactant as A, this one as B, this product as C, and this product as D. All right, so let's just imagine I assigned these variables to each one of these things. The other thing I want you to think about here is it doesn't happen to be the case today with this reaction, but we would normally have coefficients in front of these. In this case, the coefficient of 1 is assumed, so we don't bother writing it in. But I want you to think of those coefficients as being something that we could assign a variable to. And in this case, we're going to use lowercase letters, a, lowercase b, lowercase c, and lowercase d, to represent the coefficients that would be associated with a balanced equation. All right, now this sounds strange, but you'll see it'll all sort of come together in just a moment, because when we talk about the mathematical description of equilibrium, that means we can do a generalized form. We're going to take this and I'm going to convert it into a more general format, and I'm going to then write A in front of the reactant A. So again, this represents the coefficient in front of the reactant A. And we are going to, oh actually let me change the A to a green A just to keep this consistent. And then we're going to have B with capital B. We'll have the reversible reaction, the double arrow business going on here. C with a capital C. And lastly D with a capital D. And boy, this stuff in the background is distracting. Sorry, I was watching the ball game as I was doing this Patriots Day Red Sox game, but it's on a rain delay. Muting it. All right, and then I can put a plus sign in here. So you understand this is just a generic sort of reaction that I've created here. Now, law of mass action states that you can actually have this constant K, okay? And I'm going to call it the K, the constant for equilibrium, so the KEQ for a reaction, which is a ratio of the amount of products produced over the amount of reactants consumed. All right, that makes some sense, I think you can imagine, because don't forget, you can go in both directions. You're going to have some product left over after some reactant left over after it has the reaction has taken place, and at the same time you will obviously create products. So you're going to have some ratio of products to reactants associated with a reaction. Okay, so if this is a ratio that represents the reactants and the products, and also represents the concentration of those reactants and products, we do have to take into account the coefficients, because obviously that's going to have a huge impact on how reactants will combine with one another. So this is what the law of mass action looks like mathematically. And again, it's going to look a lot like rate laws. Don't get them confused with the rate laws. Now, it's very important, even though this may freak you out to see this, it's not important for you to figure out how we derived this, how we got to this point. Just understand that if you're creating a ratio, it doesn't make a difference if you add, multiply, divide, take the square root of it, square something. If it's a ratio, ultimately all the units disappear anyway. You just want to know how much reactant we have relative to the product. And so this is how we do it. You can see here that we have taken the concentration of the products, in this case, the C and the D, and we've multiplied that together. However, we take into account the coefficients by raising this reactant, or this product, to the C and raising the D to the lowercase d, and then dividing that whole thing by the reactants, doing the same concept, A raised to the A, B raised to the B. At least mechanically, I think you can see what you would do. If you had a certain concentration associated with the A, let's say it was 3.5 molar solution going on here. Oops, let's not confuse that with a bracket. I'm going to erase this one here. Where's my erase? There we go. Okay, so 3.5, and let's say that my coefficient for that was a 2. Okay, so you would simply substitute into this area down here, the denominator, 3.5 raised to the second power. Okay, so I simply took this 2 and put it up right there. I took this 3.5 and put it inside of my brackets for the denoting the concentration. So let's look at an example. I'm going to freshen up this page here. And so first let me put together a table, not unlike what we did yesterday in the screencast, which I hope you watched. And let me first write out the reaction. Okay, we have a reaction where it's phosphorus trichloride in a gas form combining with chlorine gas to form phosphorus pentachloride. So I'm going to look at the initial concentrations of the PCl3 and Cl2, and then we're going to have the equilibrium concentrations of those two things, which include, in this case, the PCl5. Okay, so this is what the table looks like. Unfortunately, I had to sort of make it extend off the page a little bit, so make sure you've written this down. And now in green, I'm going to put a whole bunch of values in concentration in terms of molarity. Okay, so here's your data for experiments 1, 2, and 3. And I'll just shift it over here so you can get it all. You're probably going to need to pause it and write this down before I move on. Okay, so I assumed that you paused. The first thing we need to do is create our KEQ, or our equilibrium expression. And so we're going to follow this law of mass action, because that is what we're looking at here. This KEQ is called the equilibrium expression. I don't think I said that to you before. So let's take a look at our equilibrium expression here. We have KEQ is going to equal, in this specific case, remember it's always going to be products over reactants, so we only have one product. It's the PCl5. And since there's no coefficient associated with the PCl5, obviously it's a 1 right here, then we would put a 1 up here. Now you don't need to put the 1 up there, it's just assumed, so there's no point in adding that to there. And this is going to be divided by the reactants. In this case it's PCl3 raised to the first power as well, and Cl2 also raised to the first power. So this is a pretty simple expression going on here. So what we need to do is figure out what the KEQ is, the actual number. And if I were to plug in the numbers into this, what I need to make sure I focus in on is the equilibrium concentration, right? I want to know what's going on, what kind of expression we have here when this is at equilibrium, not when it's in the initial concentrations. So let's slow down for a moment and take a look at this. You can see that the initial concentrations are exactly the same, and there's no point in putting the initial concentration of the PCl5 because the initial concentration of PCl5, which is the product, right, is 0. So no point in having that in there. But once this gets to equilibrium, we'll have some loss of PCl3 and some gain of PCl5, which you can see has happened right here because we went down from 0.1000 to 0.0956 in both PCl3 and Cl2's cases, and we all of a sudden have some PCl5 once it hits equilibrium. So it goes from 0 up to 0.0044 molarity. And then we can see here the same thing is going to take place in experiments 2 and 3. Now, what's important here is that we're going to plug this first set, this experimental information right here, this first line of information or data, we're going to plug that into our equilibrium expression like so. So see how I took all this data now? All I simply did was I collected up the 0.0044, put it right here in the top because that's my products, and I took my 2.0956, and those are down here in the bottom, the product of those two multiplied together. And when I chuck this into my calculator, I get 0.48. Now what I want you to do is do the same thing for experiments 2 and for experiments 3 using this data up here. So take a moment, pause it, and take a moment to do that right now. I'm sure many of you cheated and just waited for me to do it for you, you stinking cheaters. But what you can see here is that these KEQ values, the 0.48, 0.48, 0.47, are pretty much the same. Okay? And again, you shouldn't be too surprised because this is a ratio of the products to the reactants when we're at equilibrium. So it doesn't make a difference what we start with. Ultimately, we're going to have a constant when it comes to the KEQ. It's always going to be the same. And again, it's roughly the same. When you look at this one, it's a little bit less, only because this is actual experimental data. So you never know what sort of little things have happened to make it perturb itself outside of ideal situations. Now, up to this point, we've dealt with reactions that are all either aqueous solutions or gases. And that's an important thing to consider because obviously that's not always going to be the case. Sometimes you have heterogeneous situations where you're going to have a mix of different states. The beauty of heterogeneous equilibria is that it actually greatly simplifies things. And I'm not going to go into great detail right now, but suffice it to say that when you're dealing with liquids and solids, you actually don't need to put anything into the KEQ expression. So for example, here we have the ionization of barium sulfate, and it starts off here we have a solid that turns into two aqueous ions, or two ions I should say. So you would think that the equilibrium expression would look something like this. And again, you shouldn't be too surprised. I have my products up top multiplied by one another divided by my reactants on the bottom. But in reality, it looks like this. That's it. The denominator has been completely removed, or the barium sulfate has been completely removed. Why is that the case? The key to this is a little bit strange to fathom initially. Don't forget that when you have something like a solid, the concentration is not going to change in terms of a solid or a pure liquid. The amount may change, but not the concentration. Of course, it's going to go from having some, to not having any, but if this is an equilibrium expression, you're always going to have a little bit of that solid or liquid, if it's a pure liquid, left over. So in fact, that concentration then is a constant, and if it's a constant, we can essentially build it into the KEQ piece. So it's okay. All you need to know is that whenever you're dealing with a heterogeneous equilibrium situation, if you have a pure liquid or a pure solid, you don't, or actually it doesn't have to be a pure solid, any kind of solid, then you don't include it in your KEQ expression, and this is all you have to have there. So pretty simple process there. We'll do some practice with this in class tomorrow.